The following presentation is part 3 of my MOT Power Supplier series. It's an addendum on how we connect 2 or more MOT stacks together. Now the issue has been raised because it is not clear in the previous presentation, so I compiled this to help the serious experimenter to avoid damaging your newly acquired MOTs, and you've probably connected them together, stacked them, and you don't want the risk of damaging them, or you're just unsure. Let's just say you've met all the requirements and you built 2 stacks as shown here. Okay, here is stack A and here is stack B. The terminals of A, T1, terminal 1, will have the terminal 1 on top, terminal 2 at the bottom, because we end up with 2 terminals per stack. The terminal, they're 180 degrees out of phase. Okay, so we can discharge these 2 terminals together, right? And the total combined voltage is 4,800 or thereabouts, could be as high as 5,000. Okay, and we've done the same with stack B. The primaries are hardwired. Now they could be arranged that way or straight down. It could be the other way around, but the important thing is that on each stack, that at least when you combine them, the terminals are also at a convenient location so you can connect them easily together, especially the high voltage terminals, more so important than the primary. So these are the secondary windings up here. I've just shown them here. The primary are in the center. The MOTs are base to base. So the most important requirement for combining these 2 together, these stacks, is, as you can see, the only thing that's connected at the moment is just the primaries. The cores are also just grounded there. Is to match the stacks for voltage and power. You want to match them as closely as possible to voltage and power that you can, as you did the individual units to create the stacks, as we discussed in the previous presentations. Okay, so A would be to match the stacks for voltage and power. Try to maintain a balance between each stack. Okay, it's more critical between stacks than it is between the units. So as I just said, these 2 stacks are just standing side by side. They're not actually connected together. The only thing connected is the primaries, because they're sharing a primary. You've chosen one for the active, is drawn in red, and one for the neutral. These are hardwired. Not going to touch these hard wires anymore, just as when you've created the stacks, you've created them for that 180 degree phase out of phase combination. Okay, the cores are at 0 volts because they're grounded. Okay, another thing that you want to consider is that these two units, now that they're hardwired together, is that they act like one single unit. Think of it as just one transformer. Okay, that's one, that's the other, with the two high voltage ends there and there, each one delivering 2,400 volts or thereabouts, depending on what you've chosen, what units you've chosen to create the stack. Okay, so we have a total of 4 terminals to deal with. So what do we do? How do we connect them together? Okay, the circuit diagram which just appeared here to the right describes the situation that we have at the moment. Both stacks have this situation. You can see the cores. You can see the primaries, primary 1 and primary 2, which correspond with that. The secondary winding are the big windings there. The terminals, T1 and T2. The cores are grounded at the moment. You have 2,400 volts on one side, and when it's plus on one side, it's 2,400 volts minus on the other side. And of course, because alternating current and they're 180 degrees out of phase, it reverses, maintaining a potential difference of total of 4,800 volts. But that's not what we want. In order to connect them together, we're going to have to connect the two terminals together. 2 of them, because we're going to have, we only need 2 terminals that we're going to use to work with, to connect all our projects to. Okay, so the first important thing is to connect the terminals together. We're going to have to create a new ground, take away this ground. Okay, so we're going to remove the grounds first of all. Okay, grounds are gone. The next step, we're going to remove these terminals and just connect these 2 together and create a new ground there with those terminals. By doing that, what have we done? Okay, so suddenly we have a ground. We've grounded the 2 terminals, the 2 low ones, and now we have 2 high voltage terminals. Now by grounding, of course, the other high voltage terminal, the 2 high voltage terminals, T2A from stack A and T2 of stack B, they're all at 0 volts. The power input is the same. So what's happened? The core now is at 2,400 volts. Terminal T1 is now at 4,800 volts. So by connecting those 2 lower terminals together, and the only way to raise it to 4,800 is to ground those terminals, this automatically raises the core 2,400 volts. You don't want 2,400 volts on the core. There's not much you can do about that because the secondary winding is actually connected to the core, as I've already described in the previous presentations. The winding runs very, very close to the core, so you can't actually disconnect it unless you're planning to dismantle it, so it's probably best left alone. It's not a bad arrangement. See, by having a potential of 2,400 volts on the core, you only have a potential difference, and if the voltage is 4,800 volts or thereabouts, you only have a potential difference of 2,400 volts between the winding and the core, which, as you know, it's designed for. There'll be a lot more stress between these 2 if the core was grounded. So it's not a bad arrangement. That's why I said it's not a bad arrangement. It's actually a fairly good one. The only difficulty is probably the type of enclosure that you're going to have to use, and that you're going to have to keep them isolated from the case, grounding only the terminals. So for insulation purposes, you probably don't really need any mineral oil. Of course, unless you're planning to draw excessive loads and you really want to get really good heat distribution. And if you do that, that will be totally up to you. It probably does help as well to insulate it with mineral oil, just adds to insulation. But if you use proper high voltage techniques, it's not entirely necessary. Like I said, this core or these units are actually designed for a potential difference from the winding to the core of 2400. Probably in actuality it'd be a lot more than that, but at least you know you're safe. So the second requirement, or requirement B, is disconnect the ground to the cores and connect the lower terminals 2, A and B, together and ground them. Okay? And remember, don't touch any part of this, don't touch the cores. Okay? They now have to be insulated from each other. You cannot connect the cores together either. Okay? So just because they're at, because right now the cores, you know, are at 2400 volts, you can't actually connect these two together either. Okay? So if you're thinking of connecting them together, it's not a good idea. I'll explain why that is in a minute. Okay, so now you check the terminals T1A and T1B, and you find that you definitely do have 4800 volts on each terminal. Okay. You switch the unit on, and what happens? You even bring a metallic rod to the terminals. Right? 4800 volts per terminal. You should have a total of 9600 volts now between both. Okay. So you're looking for a discharge between both of these. Everything's looking good. Okay. Now, either two things can happen at this stage. Either you'll get a discharge and you'll have 9600 volts, or you won't. And if you don't, and there's no discharge, what's going on? Alright, so the terminals aren't discharging. What's wrong? You check it again. T1 is definitely at 4800 volts. T1A is also at 4800 volts. They must be in phase. Okay? Because when one is 4800 volts and the other terminal is at 4800 volts at exactly the same potential and exactly the same time, you don't have a potential difference. You want a potential difference between both of these. You want both of these units to be 180 degrees out of phase. So this arrangement can be useful. You'll have 4800 volts coming out of these terminals at twice the current. Okay, so it can be useful. But for our purposes, we want these to be out of phase, and we want a dual-ended transformer with a total of 9600 volts in this particular case. So what do we do? Okay, it's simple. We simply reverse one of the mains input to one of the stacks. We don't touch the hardwired connections anymore. It's only the input to one of the stacks. We can choose this one or this one. In this particular case, we'll choose this one. Okay, as if by magic, these connections have now reversed. As you can see, the black wire is now connected to the active on this one, and the red wire is now connected to the neutral on this one. Okay, and what's happened suddenly? Wow, it's out of phase, 180 degrees. Okay, so when this one is minus 4,800 volts, this one is plus 4,800 volts. Okay, this also suddenly changes things a bit. This core is now minus 2,400. Okay, and this core is 2,400 plus at that particular moment in time. And voila, we have discharges.